This is Maple Lesson 5, and it is on the derivative. So we're going to start with how to define a function. So we can use any letter for the variable and any letter or any name we like for the function. We'll just call it f. And the syntax for defining a function in Maple, as we did in the last lesson, is f colon equals. That means we're assigning something to this variable f. And to be a function, we have to write x and then the arrow. And the arrow you get in Maple by a minus sign followed by a greater than sign. And let's say this is the function x squared minus 3 times x minus the cosine of x. So for example, we know if we plug in x equal to 0, we should get 0 minus 0, cosine 0 is minus 1. F evaluated at 0 is minus 1. F evaluated at pi, if pi is the number 3.14 and so on, it must be spelled with a capital P in Maple. We get pi squared minus 3 pi minus the cosine of pi. Cosine of pi is minus 1. So minus 1 makes plus 1. If we want to plot f of x, that's what the graph looks like. When you plot in Maple a function that involves a trig function, Maple will usually, the default will usually be to plot it from minus 2 pi to plus 2 pi. If we want to see this in a smaller region, say maybe from minus 2 to 2, that's what it looks like. Okay. The command to find the derivative, that is to differentiate a function f in Maple, is simply capital D of f. And if you evaluate it at x, you evaluate at x by entering D of f evaluated at x. So for example, for this function that we have here, D of f is the function x goes to this, or D of f evaluated at x is that. And if we want to plot the derivative, we plot D of f of x. And this is what the derivative looks like. It's like 2x minus 3, a straight line with this oscillation added on. In fact, it's interesting. If we want to plot together two different functions, you put the functions in curly brackets. And let's say we also want to plot 2 times x minus 3. So the derivative is 2x minus 3 plus the sign. If you plot them together, you see what's really going on This red line is just the line 2x minus 3. And when you add the sine to it, that's the blue curve, you have this little oscillation built into the line. It's actually quite pretty. So you know the derivative of x to the n is nx to the n minus 1. If you want to check, you could write a loop as follows for, let's say, n from 1 to 10 do. And I want to differentiate the function x to the n. So I have to define the function. Let's say h is x goes to x to the n. And let's compute the derivative of h evaluated at x. So for the different values of n, when n is 1, the derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x. Maybe just 2. Write n comma to make everything clear. Oops. Can't do that. Here, right here. No, that doesn't add too much. In any case, here are the derivatives of the first 10 powers of x. So if you define a function, the derivative is just, in Maple, capital D. What's the derivative of the tangent of x? Maybe I better do it differently. Suppose I define the function g equals x goes to tangent of x. And now d of g is 1 plus the tangent squared of x. Can I simplify that? No, Maple doesn't want to simplify it. But you know that 1 plus the tangent squared is the secant squared. So this simply gives us the formula, but in a different form. What you learn in this, the basic formula you learned is the derivative of the tangent is the secant squared. The secant squared is secant squared is 1 plus tangent squared. Let's take simple function like sine of x. So let me define it. F is the function, x goes to sine of x. We know the derivative of the sine is the cosine. Let's plot the two curves together, the function and its derivative. So we plot together f of x and the derivative of f at x. And that's what it looks like. You know, the sine of 0 is 0, so the blue curve is the sine. The cosine of 0 is 1, so there is the cosine. And it's very nice. You see the sine has its zeros at, that means it crosses the x-axis at minus 2 pi, minus pi, 0, pi, 2 pi. The cosine is 0 at pi over 2, 3 pi over 2 minus pi over 2, and so on. Okay. Okay. So a basic problem in calculus is to compute the tangent line to a curve at a point and to plot the curve and the tangent line together. So you remember the equation of the tangent line to a curve at a point. The tangent line to the curve y equals f of x at the point x equal a is y equals the derivative of the function at a times x minus a plus the value of the function at a. So this is the basic formula that you really need to know very well. This is the equation of the straight line through the point a comma f of a with slope, which is the derivative, because the slope of the tangent line is the derivative. So, oops. So let's do some examples. So compute the tangent to, for example, y equal x squared at x equal to 2. So let's define the function f, which is x goes to x squared. And the tangent line, I'll give it a name. I'll just call it tangent line. The tangent line is the following expression: the derivative of f at 2 times x minus 2 plus the value of the function at 2. That's the tangent line. So now if I plot together f of x and this tangent line, oops, just a curly bracket there. Perfect. So this red is the parabola and the blue is the tangent line. If I want to just look at it in this region, maybe I'll just graph it from -5 to 5. And if I want it drawn to scale, I go and I click on scaling constrained. So this is really what it looks like. Then you also put in a range of values for y. Let's say y goes from -5 to 20. So here is our curve drawn to scale. Red is the parabola, and there is the tangent line. Let's do another example. Suppose I define the function g to be equal to, I don't know, x cubed minus 5 times x squared minus 6 divided by x squared plus 3. So that's a function. The derivative is kind of a mess, but Maple calculated it. We didn't have to. If we want to plot the function g of x, looks like that, from minus 10 to 10. If we want to plot the function together with its derivative, d of g evaluated at x. Ah, that's interesting. So this red is the function, and the blue is the derivative. Suppose we want the tangent to this curve at a point. Suppose I want to compute the tangent line at the point A equal to, I don't know, 3. So tangent line is going to be the straight line, the slope is the derivative of g evaluated at 3 times x minus 3 plus the value of the function at g. So that's straight line. So now, if we plot not g and its derivative, but g and this line I've called tangent line. So here's x equal 3, and you can see how nicely that blue line is tangent to the curve. Yeah, right there. Very nice. So the red is this curve, and right here is that tangent line. It's an extremely nice fit. Okay, now in Maple, there is a difference between a function and an expression. So an expression is something of the form, well, let me just look at this. That's an expression. It's not a function. You can't say, what is this evaluated at 2 or 3 or some other number? It doesn't give you anything. And you can't, if you try to differentiate this expression, you will not get what you know is the derivative, 3x squared minus 10x. You get something gibberish that it's not right. So this isn't good. This, let's just say, is not the derivative of the expression. But there is a command to differentiate an expression. The command to differentiate an expression, which gives you another expression, is you write DIFF for differentiate, and then you plug in whatever your expression is. For example, and then you write comma X to emphasize the fact that you're differentiating with respect to X. So this is the command to differentiate an expression. And let's just see if it works. So why didn't this work? So I don't know why it didn't work a moment ago, but this is certainly correct. And now it does work. So to differentiate an expression, you use DIFF, the expression, and then the variable X you're differentiating with respect to. So DIFF sine of X is the cosine. DIF times the tangent of X. It still likes 1 plus tangent squared instead of secant squared. So, okay. So this is how to do this basic thing in Maple of defining a function, differentiating the function, and computing the tangent line to a curve at a point, and then graphing them together. And I should say, when you're doing this, you can also, you can work with expressions and not just functions. So suppose we have sine of X, and we want to find the tangent to the sine at some point, like, I don't know, pi over 4. So plot sine of X and its tangent line at the point, oops, pi over 4, at a point. So let me just write TL for tangent line. So if I'm working with the sine, let's say I'm going to choose the point pi over 2. It is, now, actually, no, for this I really should be using functions. So I'll do it, but I'll do it with the function sine of X. So you have the derivative of the sine evaluated at pi over 4 times X minus pi over 4 plus the sine of pi over 4. That's what it is. Of course, we know the sine of pi over 4 is root 2 over 2. The derivative of the sine is the cosine. The cosine of pi over 4 is also root 2 over 2. So that's the equation of the tangent line. So now if we plot together sine of X and this line, perfect. The blue is the sine function, and the red is this straight line, the tangent line. And right here at pi over 4, they're tangent. If we blow this up a little bit, suppose I plot this from X equals 0 to pi over 2. Yeah. So here you see at pi over 4, how nicely this red tangent line is tangent to the blue sine function. Okay, so that is our lesson.